All right, welcome back, and thank you for wearing a mask unless you're sipping coffee. So when we were deciding whether to do this third edition of COVID, Nuri and I, there were a few conditions that we were waiting until April to see if we could do it. The first one is to see if the COVID numbers were low enough that it would be responsible to bring so many people together. And the second one was whether David was free to give a lecture. So he was the first lecturer we invited, and more than a little of the other ones were built around your lecture. So I'm very, very excited to have you here. So David studied at Perimeter Institute with Rob Spekkens and is now in Gdansk, like all the cool kids these days. And he'll tell us about contextuality, or the way he likes to put it, non-contextuality. Exactly.
Well, thanks so much, Lydia. I have to say I'm more excited for this series of lectures than I've been for any talks in recent history or ever. And a large part of that is because the Solstice of Foundations event, I think, is really special. I was actually at the very first edition of this as a student, and so it's a privilege to be back here giving some lectures to you. And I hope that your time here will be as inspiring as mine was 5 years ago. So I'm going to be talking about one of my favorite topics in quantum foundations, generalized non-contextuality. And I'm going to tell you over the course of 4 lectures what it is, why it's our best notion of classical explainability, and how to study it systematically. Very roughly speaking, this is the topic of the first lecture, the second lecture, and then the last 2 lectures. So we've all heard this idea that quantum theory is weird and it can't be explained by any classical theory, right? That's the reason we're all here, is because we want to understand the sense in which quantum theory is weird. But what's the rigorous proof of this? What do we even mean by any classical theory? What particular phenomenon in quantum theory resist classical explanations? And in what rigorous sense? So what we really need is a principled way of dividing phenomena into those which can be explained classically and those which are rigorous proofs of non-classicality. And so at a really high level, what do we want from a notion of non-classicality? This is far from an exhaustive list, but just to get us started, we'd like it to be subject to direct experimental test. We want it to constitute a resource for various practical tasks of interest, and we want it to be applicable to a broad range of physical scenarios. So the kind of first gold standard approach to studying classicality and non-classicality is non-locality, which we heard about from Paul earlier this week. And this, kind of one of the reasons it's so interesting from the start is because it's so directly testable. You don't have to assume quantum theory. You don't have to assume determinism. You make very, very minimal assumptions, and yet you can show that there's this difficult to explain phenomenology. And then you find that this intrinsically non-classical phenomena turns out to be useful, which isn't too surprising. So then you go and you try to build protocols like randomness generation or device-independent key distribution that use non-local correlations as resources. But the problem with non-locality is it's really only applicable to a very special set of scenarios. Let's take a look at what you need to witness non-locality. You need a particular causal structure where you've got some joint state which is shared between 2 parties, and then they do local measurements on it. So in particular, you obviously have to have 2 or more systems. You have to have entanglement across those systems. The choice of measurements that Alice has access to needs to have some incompatibility, as Paul showed. You have to choose those measurements in a way that's free, so uncorrelated with the state of this joint system being measured. You have to have highly efficient detectors, otherwise there's a detection loophole. And you have to have the events in both labs be at space-like separation, otherwise there's a locality loophole. So there's really a lot of constraints on what you need to assume to witness non-locality. Let's take a look what you need now to witness the failure of non-contextuality. None of this. You don't need any of that. You can just go to any scenario you like, even the simplest one of just a preparation followed by a measurement. And even without any of these assumptions, you can test non-contextuality and look for witnesses of non-classicality. Furthermore, it's been shown in the last 10 or 20 years that contextuality constitutes a resource for a long list of things that we're interested in, like computation, metrology, and so on. And contextuality can be experimentally tested in much the same way that you can test non-locality. So I won't focus too much on experimental tests. There's a nice paper, which is kind of the state of the art, although by now it's a few years old. And as I mentioned, you don't need any of those things that you require from a Bell scenario. Similar to what you don't need for a Bell scenario, in tests of contextuality, you also don't need to assume the validity of quantum theory. You don't need to assume determinism, or that you have perfect pure states or perfect projective measurements. So these are things that are in common with Bell tests. Those are things that make this more broadly applicable than Bell tests. So this is kind of why we're interested in studying this notion. And by the end of all my lectures, hopefully you'll agree that testing this notion really tells us something about what is classical or non-classical. I'll just briefly, for those of you who know about Kochen-Specker contextuality, this is kind of an alternative approach, which in some sense was the precursor to this generalized notion. It's maybe interesting to see how it fares. So there's been a lot of controversy in the past about whether this notion is experimentally testable. Basically, one of the big problems is that it assumes determinism, and it only is defined for projective measurements. And in a real experiment, you can never actually do a projective measurement. So in some level, this notion never really directly applies to a real experiment. It constitutes a resource for sure, in the same way that non-locality does. And I'd say it's applicable to more scenarios than Bell non-locality, but it's not applicable to nearly as many as this generalized notion of contextuality. And I'll say more about the relationship between these two notions at the end of the first lecture. Okay, so non-contextuality, what is it? Well, it's a constraint on the hypothesized explanations of some observed facts at the highest level. And before I tell you what exactly that constraint is, let me tell you what I mean by observed facts. So typically we capture these within something called an operational theory. So an operational theory, I'm going to focus on, we've heard a bit about this from John already at a sort of process theoretic level, and I'll work at that level in some of the later lectures, but for now, I'm going to focus on the prepare measure scenario. And in this picture, this is a very minimalist description of what's going on, where you just make a list of everything you do in the laboratory that describes your preparation. So build a laser at a particular wavelength, shine it through a crystal of a certain thickness, and so on. And among these sort of laboratory procedures that you can do, some of them can sort of be identified as preparations. Some of them have outcomes and can be identified as measurements. And the operational theory tells you the observed probabilities, so a probability distribution over the outcomes of the measurements that were performed given the preparations that were done. So this is all very descriptive, but it's not particularly interesting. No physicist would stop at this level, or few physicists are satisfied with this. Typically, we want to go further beyond description, and we want to have explanation. But to do that, you have to make some hypotheses. You have to postulate some ontology of the world, some dynamics of the world, and try to explain these observed correlations. So the sort of traditional notion of explanation that captures what sort of classical physics was all about, and it kind of captures most realist approaches to understanding the world, is kind of well captured within a really general framework called the framework of ontological models. So an ontological model of an operational theory is based on a very simple idea that when you're doing a preparation, you're preparing some system, maybe it's an electron or a photon, but you're preparing it to have certain properties. And when you do a measurement, you're learning about those properties. So this is very kind of obvious and what we all think physics is about. We're preparing and then studying the properties of systems. And these properties can all be encoded in some object, which we call lambda, the ontic state. So for now, I'm going to assume very little about lambda. You can just think of it as a list of whatever properties you think are relevant to explaining the observed statistics. And the set of these is termed the ontic state space. And I'm not going to assume any structure to this set. You can add structure in if you like. Maybe it has some group structure or symplectic structure. But we want this to be maximally general to subsume sort of anything you can dream up. So we're just going to assume that it's a set, just a collection of the possible sets of properties of the system. So the ontic state fully describes the properties possessed by a system at a given time. Position, momentum, mass, charge, color, whatever you think is going to be useful for describing your statistics. And as I said, when you do a measurement, you're just learning something about those properties. And a useful way to think about all this is it's basically just a classical causal model, where the ontic state is the causal mediary between the preparation and the measurement. So the only features of the preparation procedure that are relevant to predicting the outcomes of the measurement are the properties of the system that passes between them. So in order to tell you how this ontological model reproduces the statistics, I need to tell you how we describe the preparation procedure and how we describe the measurement procedure within the ontological model. So a preparation procedure is represented in an ontological model by a probability distribution over the ontic states. So here's a sort of example where the ontic state space is a line and we have this probability distribution. In some particular ontological models, maybe you imagine that some agent who's doing this preparation procedure has complete control over the ontic state of the system. So he can prepare it in exactly one state of reality. In that case, this distribution will be a delta function. But in general theories, it might be that you don't have complete control over these ontic states. They're kind of like hidden variables. So depending on the theory, the precise assumed distributions will vary. But in general, we associate a preparation procedure in the operational theory with a distribution over ontic states. And these are called epistemic states, and we've seen examples of those in Matt's talk. And when you do a measurement, well, depending on the true states of the system, depending on lambda, conditioned on lambda, when you do your measurement, you have some probability of getting each outcome. And it may just be probabilistic, or it may be deterministic. That's up to you to decide and put it into the model. So here I'm picturing 3 different so-called response functions. So we're imagining a measurement that has 3 outcomes, 1, 2, and 3. And if the ontic state, for example, is this one, then you see that with probability 1, the first outcome will occur. These 2 outcomes never occur. If the ontic state in a given run happens to be this ontic state, then you see the first outcome will never occur, and the other 2 are equally likely to occur. So to reproduce the operational statistics then, we just apply classical probability theory. So this is just the law of total probability. It says the probability of an outcome x given a preparation and a measurement is just the probability of a particular ontic state when you do the preparation times the probability that that ontic state will give rise to the outcome of the measurement, summed over all the possible ontic states. So this, yes, question?
If you're talking about operational theories or operational things, then you cannot talk about the probability, can you? Because you only have relative frequencies, and the probability is only obtained in the limit of infinity.
Yeah, fair enough. The truly observable things will be frequencies, as you say, and the operation, we typically sort of attempt to write down an operational theory as a sort of abstractification which has some probability rule that is sort of deduced from the observable frequencies. And we typically find that you can write down some kind of simple algorithm for computing these probabilities that happens to match the frequencies. But if you like, you can think of this as frequencies. I'm not really committed to any particular view on probability theory in this approach.
The question is that what you include in your ontic description seems to be quite up to you or up to the agent, because how do you put a bound on which physical properties are relevant?
100%. That's kind of exactly the question. So this is meant to be maximally general, but it wouldn't be very interesting if we left it at that. We're going to say, like, part of what generalized non-contextuality is about is saying, here's a property you should demand of these models further. And you might demand other properties like locality and so on, and then you try to see how far you can get. Because when you add these further structure, further principles, and so on, then you constrain the set of correlations which you can actually explain in such a model. And maybe you find that you can't explain the observable correlations, and that's kind of where we're going. Okay, so with this kind of background framework in mind, we can talk now about what non-contextuality is. So it's a property of an ontological model of an operational theory. In particular, your ontological model is said to be non-contextual if it satisfies the following property. So whenever you have experimental procedures in the operational theory that are observationally equivalent, what John called operationally equivalent, then they should be represented identically in the ontological model. And we'll make this sort of mathematically precise as we go along. And I'll do that first by example, and then we'll kind of formalize things later. So let's look at non-contextuality for preparations. So here's my operational theory kind of schematically depicted. We've got a whole bunch of preparation procedures we can do in the laboratory and a bunch of measurement procedures. And imagine that I happen to find that 2 of these preparation procedures give rise to all the same probability distributions over outcomes of the measurement m that's performed for all measurements m. So that was what John called operational equivalence, and we'll denote it by this little twiddle symbol. And so now you can go through your operational theory and group together all the things you can do in the laboratory in these operational equivalence classes. And if you have two procedures in the same equivalence class, we say that the information which distinguishes them is the context information. And John already mentioned a quantum example of this. So if you have different pure states that mix, or different states of any sort that mix to the same density operator, those are operationally equivalent. So in particular, if I take the 0 state and I mix it with the 1 state with uniform weights half-half, well, that's the same density operator as if I mix the plus and the minus state. So if I go to the laboratory and I try to implement this mixture or this mixture, those are two completely different things you do in the laboratory, right? To prepare these pure states is a macroscopically distinct experimental configuration from preparing either of these pure states. So it's completely different in the lab, but nonetheless, no matter which of those mixtures you do, there's no measurement that can tell the difference between them, because any measurement on this will just be a function of the maximally mixed state by the Born rule. So in quantum theory, we have this nice property that two preparations are operationally equivalent if and only if they're represented by the same density operator. That just follows from the Born rule directly. So we see then here that each of these sort of operational equivalence classes is associated with a distinct density operator. So now we can talk about what a preparation non-contextual model of this set of preparations would look like. Well, non-contextual means independent of the context. So here, these two procedures are the same up to context. They're only different because of their context. So in a non-contextual model, their representation as a probability distribution over the ontic states can't depend on whether you do P1 or P4. They're represented in the same way. So the representation of each preparation does not depend on the context. In contrast, in a contextual model, the representation of each preparation does depend on the context. So in this case, you could have one epistemic state for P1 and a different epistemic state for P4. So I'll put these on the same slide so that we can kind of contrast these different sorts of representations of our operational theory. The non-contextual explanation explains why the two preparations are in the same equivalence class. Of course, there's no measurement that can tell which of these you've done because they're both sampling from the states of reality in exactly the same way. In contrast, the contextual model kind of is lacking this sort of explanation. The only way that you can explain the fact that these two epistemic states lead to all the same statistics is if the response functions, the way that measurements are represented in the model, have some very coarse-grained features that wash out the differences between these probability distributions. So for example, consider this ontic state here. We see that it has probability 0 with one of these two preparation procedures, and it's non-zero with the other. So we see that there's a true state of the world, some particular properties of the system, which one of these procedures is preparing, and the other one, it never prepares those. So there's kind of complete ontological disjointness for that particular case. And so how do you explain that there's no measurement that can see this difference in properties? Well, the only way is to imagine that the measurements have some kind of fine-tuned functions over lambda. So let's see two specific models of just of a small part of quantum theory. So here's 4 pure states and the maximally mixed state. And we've already seen a preparation non-contextual model for these states. It's the Spekkens toy theory that Matt was discussing. So you'll recall that the ontic state space had 4 points. So there's 4 ontic states. And we had these 4 probability distributions representing the 4 pure states. And then the maximally mixed state was just the uniform distribution over all 4 ontic states. Contrast that with a second model that was invented by Kochen and Specker. In this model, the ontic state space is very different. It's the set of points on the surface of a sphere. So it's a set that's isomorphic to the surface of a sphere. And so note this looks a lot like the block ball, but it's different. Here, each point on the sphere is a pure state. Here, each point on the sphere is an ontic state. And the representation of the 0 state in this model is this kind of egg-shaped blob coming up off the top of the sphere. And then we have the probability distribution over ontic states for the state 1, plus and minus. And we can see that the first model is preparation non-contextual with respect to that operational equivalence that we mentioned earlier. Because if you mix together the 0 and the 1 preparations, you get this uniform distribution. If we mix together the plus and the minus distributions, we also get the uniform distribution. That's preparation non-contextuality. In contrast, the uniform mixture of these two distributions is shown here, and the uniform mixture of these two distributions is shown here. And clearly, this distribution is not equal to this distribution. So this is a preparation contextual model, and as I mentioned, it doesn't naturally explain why it is that the statistics in quantum theory are the same for these two mixtures. Question?
Sorry, what's the blob?
The blob, this red thing?
Yes.
So I haven't defined it for you precisely. The mathematical details won't be necessary for us, but it's supposed to be a three-dimensional function over points on the surface of the sphere. So you see, for example, here, if you do the minus preparation, what this distribution tells you is that the ontic state that's most likely to occur, so the highest value of this function, is the ontic state that's sort of on the rightmost point of the sphere. And this ontic state will never occur because it's assigned probability 0 by this red function. And maybe it's also worth pointing out, like, let's think about what's the ontology that these two models are postulating. Well, this first one, you remember, as Matt talked about it, you could think of it as an occupation number that's binary, like top versus bottom, and a phase which is binary, right versus left. So that the ontology here is just two binary variables. Whereas in contrast here, you might think the point on the sphere is sort of picking out a direction. So maybe this is how you would represent a classical spin that just has some direction in 3 dimensions. So they're very different kind of attempted hypotheses for what's going on in a quantum scenario. And you can, like I said, you can kind of adapt the ontological models framework to whatever sort of explanation you think will work best. And then you can look what sorts of properties does my explanation have. In this case, we see this explanation has the property of non-contextuality. This explanation is contextual with respect to this operational equivalence among these 4 pure states. For measurements, everything's about the same. We can group together the measurement procedures in our laboratory into operational equivalence classes. We denote that with a tilde. And these are defined as measurements that give the same probability distribution over outcomes for all possible preparations P. So again, we have measurements that differ by context, and let's see an example from quantum theory. So imagine 2 different coarse-grained measurements. So you go to the laboratory, and so we're in a 3-dimensional Hilbert space here, you either implement the projective measurement onto this particular basis, psi1, psi2, psi3, or you implement a measurement onto the basis psi1, psi2 prime, psi3 prime. So notice here the psi1 projector is the same for the 2 measurements, but the 2 and 3 projectors are rotated in this plane, so that's why I'm labeling them with primes. So these are 2 different projective measurements, and now I want to imagine coarse graining over the 2-3 outcome and coarse graining over the 2', 3' outcome. If I do that, we'll notice that the coarse graining of the projectors onto the 2 and 3 state is just the projector onto this blue subspace. And the coarse graining of the 2' and the 3' projectors is also just the projector onto the same subspace. So when I coarse grain these 2, I get the same thing as coarse graining these 2 projectors. So in both cases, if I implement this 3-outcome measurement and coarse grain, or implement this 3-outcome measurement and then coarse grain, both of those measurements are described by the same projective measurement that says, am I in the psi1 state or in the orthogonal complement? So these 2 measurements are operationally equivalent after you've done the coarse graining. And in a non-contextual model, each of these measurements, well, it's a binary outcome measurement, so there's 2 response functions, one for the first outcome, one for the second. In a non-contextual model, these 2 response functions have to be the same for the 2 different measurements in question. In a contextual model, you'll have 2 response functions for the first measurement and 2 different response functions for the second measurement. So that's what a measurement contextual model looks like. For transformations, we'll talk more in later questions. Yes?
I'm sorry to bother you again with the same question, but there are a lot of infinities in my mind in this definition. For all preparations involves an infinity. Each of your measurements requires infinite precision. How can you say that?
These are all good questions, and I will address all of them in due course, if you can hold on to it. So we do have like solid answers to those questions. But for now, you'll just have to take me on faith. But they're very good questions. Okay, for transformations, everything is defined in a sort of analogous fashion, which, again, we'll come back to later. For now, I want to keep things simple. So to summarize on one slide, we have some observational stuff, some operational equivalences. These are just facts that you can go check in the laboratory. Do you think these two procedures are operationally equivalent? Well, go do as many possible measurements as you can and try to falsify that. Go see if there's any measurement that can distinguish them. If not, then you start to accumulate evidence that these procedures are operationally equivalent. And then if they are, we say, in your hypothesized explanation, if that explanation is to be non-contextual, then they better have the same stochastic representation. Okay, so what I'm going to try to convince you of over the course of these lectures is that this turns out to be a rigorous way of dividing phenomenon into those which can be explained classically, that is, by a non-contextual ontological model, and those which cannot, which we'll take to be non-classical. And you can come up with rigorous proofs of that some set of phenomena can or cannot have such a model. So if you have some experiment or a theory or a set of phenomenology, and it's classically, we say that it's classically explainable if you can reproduce it in one of these non-contextual ontological models. Alternatively, if you can prove mathematically that there's no possible non-contextual ontological model that reproduces those predictions or that experiment or those phenomena, then you have a proof of non-classicality. So this is kind of like what Bell did. He took essentially the ontological model's framework, he added in an assumption of locality, and he came up with a proof that you couldn't reproduce all the quantum statistics. We're going to do exactly the analogous thing here, where the assumption is non-contextuality instead of locality. So in the third lecture, I'll actually go through and explicit such proof, but that's sort of the subject of the whole lecture. For now, I'm just going to kind of outline for you at a high level what such a no-go theorem looks like. So you start with whatever circuit you're interested in. And again, I'm going to focus on the simplest case. So you've got some particular quantum states and some particular effects, quantum POVM elements. Now, really, nothing that I'm saying throughout all of my talks is actually specific to quantum theory. You can do all this for operational theories and generalized probabilistic theories beyond quantum theory, but I'll just stick with quantum examples typically because it makes the point clear. So maybe you have some particular scenario you're interested in with these 4 quantum states and those 3 POVM elements. And the first thing you do, if you want to study non-contextuality, is you figure out what are the operational equivalences that hold among these. So I'm still sticking with my simple example where you have a uniform mixture of 2 states. Here it's phi and phi bar, which is the same as the uniform mixture of psi and psi bar. And it turns out that's the only operational equivalence among these procedures, which is why I've chosen this really simple example. In general, there will be more complicated, but it's not too hard to find out what the operational equivalences are. And then from this operational equivalence, if you couple that with this assumption of non-contextuality, then you get constraints on your ontological model. So in particular, preparation non-contextuality tells you that the uniform mixture of the representation of state phi with the representation of state phi bar, so that's the uniform mixture of this probability distribution labeled by phi and the one associated to phi bar, has to be equal to the uniform mixture of the representations of psi and psi bar. So we get a kind of constraint. And I want to emphasize that this operational equivalence here is something, again, that you can go test. It's kind of free for all to judge for themselves. Whereas this thing here can't be tested. It's a fact about this hidden variable model, this ontological model. So there's no direct test whether this holds or not. It's what follows from the assumption of non-contextuality. And when you take this assumption and you try to reproduce the observable phenomena that you get when you sort of implement these measurements that you can construct on these quantum states, you find that there's bounds on the observable data. So you can't reproduce arbitrary data once you have this non-trivial constraint here. So here's this observable data for this scenario. The bounds, what they look like, very much as in Paul's talk, we saw Bell inequalities. Now we have non-contextuality inequalities, where it's kind of some linear functional on the set of observed correlations, and you can find a bound on those. And so these bounds, these inequalities, can be shown to always form a polytope. So there's a non-contextual polytope, which is kind of the analog of the local polytope or the Bell polytope. So each point in this space, maybe it's a high-dimensional polytope, here it's a simple two-dimensional one. Each point in the space is a set of correlations that can be observed. And if you find a correlation which is outside this polytope, so it violates one of these inequalities, and in this case you have a facet inequality here that's clearly being violated by this point, then that's a witness of the failure of non-contextuality. It shows that this assumption here must be false, and so preparation non-contextuality must be false. And so I'm arguing that that is a rigorous proof of non-classicality. And so you can look in particular at the set of quantum correlations, and it's not hard to show that that set is strictly larger than the non-contextual set, and it's not a polytope, but some set which Vicky will tell us a lot more about. And as I've mentioned, these proofs of non-classicality don't actually rely on the correctness of quantum theory. If there's some other theory, you could also check if that theory can achieve correlations outside the non-contextual set. You can even ask, what's the sort of maximally contextual theories? What's the largest logically possible set? And again, Vicky's going to tell us more about those things later on. But I want to jump to Kochen-Specker non-contextuality, which is going to lead us into the question of why is non-contextuality a good assumption, which I haven't said much about yet, but I will in a minute, and also the next lecture will have a lot about that as well. So Kochen-Specker non-contextuality can be defined as, if you like, measurement non-contextuality, as I defined it earlier, plus outcome determinism. And with one further caveat, which is that it's only really defined for projective quantum measurements. It doesn't make sense for other kinds of quantum measurements. So imagine that I have some 3-outcome projective measurement, like this. In an ontological model, we associate to each of these projectors onto these 3 ontic states some response function. And what it means to assume outcome determinism, it means that given an ontic state, the outcome is determined. This is just an assumption of determinism. So here, you see if this is the ontic state, the first outcome will always occur. In fact, for all ontic states in this region, the first outcome will always occur. For all ontic states in this region, the second outcome, and here, the third outcome. There's no non-trivial probabilities. It's all probability 0 or 1. So the response functions are 0, 1 valued functions. So that's the determinism part of this assumption. What about the measurement non-contextuality part? Well, it's a bit similar to before. So a given projector can appear in many different measurements. So let's focus on this projector onto the psi1 state. And we saw this measurement before. And we also saw this measurement before, where the same projector appears in these 2 different measurements, but the sort of second and third projectors in the measurements are different. So we see this single projector, psi1, appearing in 2 different measurements. In a Kochen-Specker non-contextual model, every projector is associated with the same deterministic response function, which I'm calling chi here, regardless of how it's measured, regardless of the context, or equivalently, regardless of which measurement it appears in. So in other words, the representation of this measurement in the ontological model had better have the property that the response function for the projector onto psi1 is exactly the same as the response function for the first measurement. Same projector, same response function. In contrast, of course, the last 2 outcomes, well, they're different, right? So they're different projectors in quantum theory, so there's no reason, in fact, they can't be represented by the same function over ontic states. So you see that these 2 functions are different from those 2 functions. But if you coarse grain these 2, then you have to recover the coarse graining of these 2. And you can see that that's satisfied here. So this is what the non-contextuality part of Kochen-Specker non-contextuality means. And another way of thinking about it is, let's see, do I write this? Yeah, maybe I'll just mention. So for this particular ontic state, you see that the outcome which occurs is always the same. It's the first outcome. For this ontic state, we can get different outcomes. So it's not like the outcome of these 2 measurements always has to be the same. Of course not, because they're different measurements. We're just saying the ontic states which lead to the first outcome are the same in both measurements, because it's only the first outcome that's operationally equivalent in this measurement. OK, great. So what Bell and Kochen-Specker proved independently was that there's no hidden variable model that's non-contextual in this sense. that can reproduce the quantum predictions for Hilbert spaces of dimension 3 or greater. And I'll just give you a quick proof of that because it's not too hard. So it turns out in quantum theory you can find 9 projective measurements using only 18 projectors, where each projector appears in 2 different bases. So this is what the particular construction looks like. We have 18 projectors, pi1 to pi18, and the sum of the first 4 is identity. So the first 4 projectors form a valid POVM. So here we see these first 4 projectors in a loop. That just signifies that that's a valid projective measurement. Similarly for the projectors 4 through 7. And so we have all these conditions, these 9 different projective measurements, where each projector appears in exactly 2 of the measurements. So in a Kochen-Specker non-contextual model, for each ontic state in the model, that ontic state has to tell you whether or not a given projector will be the outcome that occurs. So we have to have a value, a probability assignment to these different outcomes, which has precisely a single 1 for one of these 4 outcomes in a loop, and it's 0 for all the rest. So for example, here I'm saying, if you implement this measurement here, you'll always get this outcome here corresponding to pi15. These 3 are assigned probability 0. So that's the determinism part of Kochen-Specker non-contextuality. And the non-contextuality part of Kochen-Specker non-contextuality says the value 0 or 1 assigned to this pi1, for example, has to be the same when it's measured in this context or when it's measured in this context. Those are 2 incompatible measurements. You have to pick one or the other, but the value we're assuming assigned by a given ontic state has to be the same, regardless of which measurement you do. So in other words, we can just assign a value, 0 or 1, to the projector pi1, and I'm not labeling that. In principle, that value could be labeled by the basis, sort of this basis up here or this basis here, but there's no such label because we're assuming non-contextuality. So then in a Kochen-Specker non-contextual model, it better be that the values, like I mentioned, the sum of these 4 values assigned to pi1 through pi4 had better be 1 because only and exactly one of these outcomes has to occur. So we get this set of linear equalities from Kochen-Specker non-contextuality. And it's not hard to see that there's no satisfying this set of linear inequalities. How do we see that? Well, if you sum together the right-hand side, there's 9 of these bases, so you get 9 times 1 is 9. On the left-hand side, remember that each projector appears exactly twice. So we have pi4 appears here and here, pi7 appears here and here, and so on. You can just see that each one appears in exactly 2 of these equations. So we end up with 2 times an integer, because each of these is valued 0 or 1. And this is clearly not satisfiable. So there's no assignment of 0 and 1s here that can satisfy this graph. And you can also kind of play around with it graphically and just see like this projector here has to be assigned value probability 0 because this one was assigned probability 1. But if this is 0, well then we have all 4 of these in this basis, in this loop, would be assigned probability 0. So that would be saying for this ontic state, no outcome will occur, which of course then your model is problematic. As I mentioned earlier, if you relax this assumption of non-contextuality, well now we're imagining that the probability assigned to pi1 can depend on the basis. So here we see pi4, it appears in the first basis, which I'm now calling b1. It also appears in the second basis. Oh no, I messed up the labeling. It appears in the 6th basis. This should be like a, wait, 4, 5. Okay, my labeling, oh, okay, this is pi4. Yeah, it appears in basis 1 and basis 2. So the 2 values assigned to it could in principle be different if we assume that it's a contextual model. And then now we have none of these values appears twice, and you can just show that there's many possible solutions to this equation if you relax the assumption of non-contextuality. Another way out of this no-go theorem, however, you could actually hold on to non-contextuality if you give up on determinism. So what if we imagine that the model for a given lambda doesn't tell you that one outcome will always occur, but there's just some probability with which each outcome can occur? Well, in that case, it's easy to come up with a probability valued assignment to this graph. So we can just say that, for example, every outcome is equally likely to occur. So if you do this measurement, each outcome has a quarter probability. If you do this measurement, each outcome also has a quarter probability. So you can see that the assignment for this projector is non-contextual, and for all of them is non-contextual. So this is a kind of loophole. You can actually keep non-contextuality in the Kochen-Specker sense if you give up on determinism. And that's kind of generic. This is just one example, but there are many indeterministic probability assignments. They're not all this trivial. But it turns out all of these can be ruled out by the generalized notion of non-contextuality. So in some sense, there is a determinism loophole for Kochen-Specker contextuality. There is no determinism loophole for generalized non-contextuality. And this is one of the reasons why we prefer this approach. And in particular, this is just a useful fact, which I won't say more about, but it turns out that preparation non-contextuality can be used to show that you have to have outcome determinism if you have perfectly projective measurements. And that's how you can rule out these kind of indeterministic assignments. It's actually by appeal to the preparations that you can justify determinism. Okay, but so in some sense, the reason I got into all this, aside from kind of the historical interest in Kochen-Specker contextuality, is because even back when Kochen and Specker were thinking about non-contextuality, or at least when Bell was, people were asking, why is this a reasonable assumption in the first place? In particular, I'll focus on the Kochen-Specker case first. Just because this projector appears in two different measurements, why do you think it has to behave in the same way in the model? Why does it have to be that in the model you're measuring the same property? In particular, these two measurements are incompatible. They're necessarily distinct experimental devices. Two different macroscopic devices have to be set up to do these two measurements. So why should you expect the value assignments for the first outcome of these two distinct apparatuses to be the same? As Bell put it, these different possibilities require different experimental arrangements. There is no a priori reason to believe that the results should be the same. The result of an observation may reasonably depend not only on the state of the system, including the hidden variables, but also on the complete disposition of the apparatus. So this was kind of the challenge. He said, I've got this no-go result, but how interesting is it really? Because you can get out of it just by saying, OK, the measurement outcome depends on the apparatus. Is that really so bad? And to my mind, the only really satisfactory answer that has been given to this question was by Rob Spekkens, who's the person who introduced generalized non-contextuality. And what he said is, well, you should expect the value assignments to be the same, and here's why. Because it's the best explanation for why the different measurement devices give rise to exactly the same statistics for all possible preparations. It's kind of an appeal to the simplest possible explanation. And it can also be motivated by Leibniz's principle of the identity of indiscernibles, which, roughly speaking, can be stated something like this. So if you have a difference in setups that's not distinguished, if it's in principle not distinguishable in the observable phenomenon, then it shouldn't be distinguished in your ontological picture of the world either. So this is kind of a principle which guides you in constructing good theories. And it's been successful in constructing good theories in the past. So Einstein used it kind of repeatedly throughout his career. So for example, he used it in the development of special relativity to rule out, he came up with an argument against the ether. So he said, imagine there's some ether permeating space, and we have a ring, a coil of wire, that's fixed with respect to the ether. But we have a magnet moving with respect to the ether. And then he said, alternatively, imagine a different scenario where the magnet is fixed and the wire is moving. And he said, look, the observable phenomena here, the current induced in the wire, is exactly the same. So this ether, it makes these two scenarios look different because it's kind of a privileged rest frame. But if you get rid of the ether from your ontological picture of the world, then suddenly these two situations look exactly the same at the ontological level. And that explains why everything that happens at the physical level, the electrons moving around, the magnetic fields, et cetera, is independent of which of these two situations you're in. So this was kind of the motivating idea behind much of relativity theory. And similarly, he used the same kind of arguments again to construct his general theory of relativity. He said if you do experiments in some accelerating reference frame, or if you're fixed in some gravitational field, there's no experiment that can tell the difference. So we should postulate that these two operational scenarios are really referring to the same ontology, namely some curved space-time. Both of these are subsumed within a single ontological picture of the world. So you can find still more examples where Einstein and others have used this kind of idea of Leibnizianity to do good physics in the past. So this is one of the sort of nice a priori motivations for assuming non-contextuality, is it's an instance of this idea from Leibniz. And so this was all a response to the Kochen-Specker, the question of why you should assume Kochen-Specker non-contextuality, but it's also the exact same reason why you should assume generalized non-contextuality. So the justifications for Kochen-Specker lead you to the generalized notion as well. So if you think the first is well motivated, you should think the second is. But the generalized notion has a number of advantages. So as we already sort of mentioned, the Kochen-Specker notion only applies to projective measurements, whereas the new notion applies not only to noisy measurements, but also to preparations, transformations, fragments of circuits, arbitrary scenarios. And we don't assume determinism in this generalized approach. And as I'll say more in the next talk, there's kind of a long list of other reasons why non-contextuality is a good notion of classicality. But I think we'll take a break for a bit before we get into more of those reasons.
Let's take a 5-minute break and restart at 11:30. Okay. David?
Okay. Is my mic still well adjusted? I'll take that as a yes. Okay, so in the second lecture, I'm actually going to take a very different perspective on non-contextuality. It's kind of a geometric. So previously it was a bit more algebraic, classical probability theory. Now I'm going to take a geometric perspective using the framework of generalized probability theories that John talked some about. And I think this is my favorite lecture of the 4, so I hope you will also enjoy it. And it kind of helps us see why, I'll give 1 or 2 good reasons why, further reasons beyond Leibniz's principle, why generalized non-contextuality is a good principle for a model to have, and why it's our best notion of classical explainability. So in some sense, this is kind of a web of evidence. There's no sort of single reason, which I think is at the core of it all. There's kind of a list of a priori motivations. This is going to be the subject of the talk today, so I'm going to show that there's a notion of classical explainability of a GPT, which you can kind of independently motivate, and then you can prove it's equivalent to the existence of a non-contextual model. Similarly, there's a notion in quantum optics of the existence of a positive quasi-probability representation. And if one of those exists, we say that the experiment has a classical explanation. And that can also be shown, in some sense, to be equivalent to non-contextuality. And I mentioned Leibniz's principle. Then there's the fact that generalized non-contextuality subsumes some other notions as special cases. So we already discussed Kochen-Specker non-contextuality. Bell inequality violations are also violations of generalized non-contextuality, which maybe we'll have time to talk about in the last lecture. Anomalous weak values have been put forward as a kind of surprising notion of non-classicality. They're also proofs of generalized contextuality. Furthermore, this notion of non-contextuality has a number of key features which we kind of like for any notion of classicality to have. I already mentioned it applies to arbitrary scenarios without assuming the correctness of quantum theory. You can test it experimentally. Furthermore, when you have sufficient noise or coarse graining or decoherence, you can prove that you always recover classicality. Two minutes ago? Yeah. Oh, just the dual? Maybe I can go back to here. So, right, there's a class of GPTs, which essentially everyone who's studied GPTs agrees is a representation of something classical. These are called simplicial GPTs because the state space is a... Shall I?
Gonna be on a leash.
We'll see if I can behave. Not so far.
All right.
Okay, thanks. All right, so in such theories, the state space is a simplex, the effect space is the dual of the simplex. And why is it that everyone agrees these are classical theories? Well, it helps to label the axes suggestively. So let's take the vertices of the triangle to be the unit vectors, right? 1, 0, 0, 0, 1, 0, etc. And then it's not hard to see that the vertices of the cube will be all the 0, 1 valued vectors. So if you take inner products of anything in that cube with anything in this triangle, of course, you'll get values between 0 and 1. And now when we look at this, so let's focus just on the normalized states. So sort of this is the completely unnormalized state, but we're just going to focus on those states which have the right normalization. So this is the triangle, the set of normalized states, and the set of effects is kind of one dimension higher. And the reason that everyone agrees this is a classical theory is because it's just a classical statistical theory. So each point in this triangle is isomorphic to a probability distribution over some set of 3 classical states. So clearly these 3 points here are classical probability distributions. But furthermore, and so we can think of those as the classical states of the system, the ontic states, if you like. But furthermore, each point inside the triangle, like this point here, is the equal mixture of these 2 probability distributions. So it's this one. This point here is the uniform mixture of all 3 ontic states. And furthermore, every probability distribution over 3 points has a representation in this. So there's kind of an isomorphism between the set of probability distributions over 3 ontic states and the points inside this triangle. So what that means then is that each mixed state, like this one here or this one here, in this theory decomposes into pure states in a unique way. So if my state of knowledge is this one here, I can always think of it as there's a true state of the system. It's always one of these 3 red ontic states, but I just have uncertainty about which one there is. In quantum theory, this isn't true, and there's no sort of unique way to just think of classical uncertainty over some true states of the system. But in this kind of simplicial theory, one of the 2 key properties is that you can always imagine that the real state of the world is one of these 3 ontic states, and any mixed state can just be uniquely interpreted as classical uncertainty. And furthermore, in these theories, you can show that all logically possible measurements are physically possible, and furthermore compatible. So in other words, there's a single measurement that can tell you exactly what the true state of the system is. So if the state happens to be one of these 3, you can always discriminate those perfectly. And if you have uncertainty, you can always resolve that uncertainty by sort of a single all-powerful measurement. And again, that's not true in quantum theory, but that's exactly what we think of in classical theories, that there's no fundamental restriction on learning what the state of the system is. So for these reasons, people think of simplicial theories as classical. Simplicial implies classical. Fine. But what's only been recognized a bit more recently is that there's a broader class of GPTs which can also sensibly be said to be classically explainable or classical. And so, in particular, what about subtheories of a simplicial theory? So GPTs whose states and effects are a strict subset of those in the simplicial GPT. So here's the simplicial GPT in black again. What if we instead think about a GPT living inside it? So maybe the convex set of states in this blue region and the convex set of effects in that blue 3-dimensional region. What about that GPT? Is that GPT classical or not? Well, let me first just note and be very explicit that if you're writing down this blue GPT and saying, this is my description of the world, you're explicitly committing to the fact that this probability distribution where you know exactly that you're in this ontic state is ruled out. You're saying there's some in-principle restriction on what states can be prepared, what classical probability distributions can be prepared. And similarly, you're ruling out some of the logically possible effects. That's what you're postulating when you consider some GPT inside a strictly simplicial theory. So this is kind of like the epistemic, it's exactly like the epistemic restriction in the Spekkens toy theory, which said that certain states of knowledge about the ontic states are just forbidden by assumption. And the intuition is, well, these feel like they should be classically explainable as well, because you're just picking out a subset of these classical states and effects. And you can always still imagine that the vertices do correspond to the true states of the system in the world, and we're just adding this minor thing on top of that, which says, but you can't always perfectly control or measure or learn those ontic states. So the ontology is the same as in a simplicial theory, but you can't always prepare, measure, or know the ontic state. So a bit more formally, although still not full formally, a GPT is simplex embeddable if there exists a linear map taking states into a simplex, so taking these blue states into the triangle in this case, a linear map taking effects into the dual of the simplex, such that probabilities are preserved under the joint application of these two maps. So it's kind of just a way of mathematically capturing the intuitive notion in this diagram here. So my claim is then that simplicial implies classical, but simplex embeddable should also be viewed as classical. And to sort of just have some kind of terminological distinction, I'll refer to these as classically explainable. And I'll sometimes refer to the simplicial stuff as strictly classical, because there is a difference between assuming there's an epistemic restriction or not. So I'll call this strictly classical or classically explainable. And now the question becomes, so which GPTs are simplex embeddable? That is, which ones have classical explanations? If I just throw one at you, you maybe can't tell immediately, could I find a three-dimensional simplex that fits around this ball such that the dual of that simplex fits around this top-shaped object? Well, it's not immediately easy to see, but this is the sort of thing you can study mathematically and geometrically, and you can come up with no-go theorems that say this GPT is not simplex embeddable, therefore there's no classical explanation for it. So if I just give you a GPT like this one, can you fit it inside the simplicial GPT? Well, at first glance, this is too large to fit inside the triangle because I made it bigger than on the last slide. Whereas this looks like it will fit in easily. But you can't just be that naive. You have to think a bit harder. So it's possible to jointly rescale states and effects. So if I make every state in the state space smaller by a uniform factor, and I make every effect in this space bigger by that same factor, then the inner product of these two will be the same. So this GPT, even though I've rescaled things, is really an equivalent physical theory. And now it looks a bit more likely to embed, but you also might have to jointly reorient the states and effects to fit them in the simplex. So maybe you rotate all those vectors by the same amount. Again, that's not going to change the probabilities, so it's not changing the physical theory. It's just changing your kind of explicit representation of it. And now if you do the right rotations and rescalings, maybe you can find that it does in fact embed inside a simplicial theory, and then you say, aha, I found a classical explanation. I can always think of there being some, in this case, some ontology with 3 ontic states. Every preparation is just represented by a classical probability distribution over those ontic states, and so on. But, yeah? In some sense, the axes don't really matter. What I'm sort of trying to say here is that your particular coordinatization is kind of like a gauge degree of freedom. It's not relevant to the actual physical theory. I've had to sort of implicitly, maybe just think of the board as, think of vertical as the z-axis and horizontal as the x-axis and so on. But in some sense, I'm trying to present things in a more coordinate-independent way. So it's still not even quite so simple because, in fact, you can apply any linear transformation to the state space that's invertible and then apply the inverse transformation to the effect space. And so that will include even more complicated things like where you skew, maybe you like smash everything up and to the right, and it will change the sort of shape as well. But then you change this effect space by the inverse transformation, and when you take the inner product, again, the inverse map will cancel with the map, and so you'll get the same probabilities. So this is all just kind of annoyances for dealing with the sort of gauge degree of freedom in defining GPTs. But you can deal with all that just by the definition of simplex embedding. I'm just trying to give you some intuition at this point. And perhaps the biggest thing that we need to note here is that in this picture I've given you, I've assumed that the simplex is in the same dimension as the GPT, right? These are both 2-dimensional state spaces, 3-dimensional effect spaces. But in general, who says that there's only 3 ontic states in your ontological model that's representing your GPT? Maybe there's many more ontic states. So you have to look at high-dimensional simplices embedding lower-dimensional GPTs in general. And that makes this much harder because it means, that in principle, a priori, there's no bound on the dimension you have to look at. So you have to keep checking higher and higher dimensions to see if there's such an embedding. But it turns out you can prove after the fact that you only have to go up to a certain amount, so the square of the GPT dimension. So it's not actually so bad, but it definitely doesn't have to be the same dimension. And I think we'll say a bit more about these dimensional issues later. And I'll just point out that deciding if a GPT is simplex embeddable or not is a linear program. So it's something that you can fairly efficiently compute. And so even though you have to deal with all these kind of annoying caveats at an intuitive level, at a computational level, it doesn't make it too difficult. OK, so one just kind of cute conceptual insight that we can already draw from this approach is that if you take a GPT and you apply depolarizing noise, it will always become classical in the sense of simplex embeddable. So here's an example of a GPT which is not simplex embeddable. Again, you can't really tell just from the picture because you'd also have to check higher dimensional simplices. But let's say it's not simplex embeddable, and we illustrate that like this. We can always, so what depolarizing noise does is we're going to apply it to the states, and it just shrinks all the states towards the maximally mixed state. That's the definition of depolarizing noise. So if you do this kind of shrinking of states, at some point, it's going to embed inside the triangle. So what you do is you use that joint rescaling I mentioned earlier to make sure the effects are properly embedded in the hypercube. To do that rescaling might force you to make the state space really, really big, and then it doesn't fit in the simplex. But then when you start applying depolarizing noise, the state space gets smaller again until it embeds. So you can always recover simplex embeddability under depolarizing noise. And it's just kind of clear geometrically. And then you can define a measure of how non-classical your GPT is by how much noise does it require, does it have to undergo before it becomes simplex embeddable or classically explainable. So that was all sort of stated without explicit reference to non-contextuality. And now I'm going to show you that it's actually pretty easy to see that it's equivalent to non-contextuality. So these two notions of classicality, one of them was about ontological models of operational theories. The second one was kind of a geometric approach that applies to generalized probabilistic theories. And they're in fact equivalent in a sense that we'll go through now. So the first thing to note is something that I've kind of already been hinting at repeatedly, which is that a simplex embedding of a GPT is just an ontological model for it. So remember we said these vertices, you can basically think of them as the classical states or ontic states, and each point inside this triangle is an epistemic state. It's a valid probability distribution over the ontic states. And each point in this space is a valid response function. It's a function over the ontic state space that's valued between 0 and 1. And so if we consider a GPT that's simplex embeddable, well, it's just picking out a subset of those epistemic states and response functions, which it says are physically possible to implement. Not all of the logically possible ones are physically possible in this simplex embeddable GPT in blue here. But the theory tells you which ones are possible and which ones are not. And you can always interpret them in the obvious way. So the epistemic state for a given GPT vector, so you can think of the GPT as like the operational level. And then in the ontological representation, we need to represent each GPT vector with an epistemic state. How do you do that? Well, you just take the vector of its coordinates. So this picture is kind of a dual purpose. You can interpret it completely in the GPT framework, where each vector, the coordinates of that vector are just a particular representation of the GPT state. Or you can equivalently take the exact same picture to be representing the ontological model, which represents the GPT. Precisely because it's simplex embeddable, each of these points has this dual interpretation. These points are all valid probability distributions. And similarly, the response function for a given GPT effect is, again, just the vector of its coordinates within the in the space. And as you'd expect, the inner products in the GPT, the predictions of the GPT are reproduced by just the inner product of an effect vector with a state vector. And in the ontological model, we expect it to be similarly a kind of inner product between the epistemic state and the response function vectors. And because the vectors are defined to have the same coordinates, this equality here is true by construction. So hopefully that's clear. It's just two ways of viewing the exact same picture. And so a GPT is simplex embeddable if and only if it admits of an ontological model. Strictly speaking, I guess I only proved one direction, but you can look at it and convince yourself that the converse is true as well. So the next thing that I'm going to argue is the key for connecting this all with non-contextuality. And it's that a GPT admits of an ontological model, any ontological model, if and only if the operational theory, which is described by the GPT under quotienting, which John talked about, admits of a non-contextual model. So in the first case, we're talking about ontological models of GPTs. In the second case, we're talking about particular ontological models, namely the non-contextual ones, of operational theories. And there's this if and only if between these two. And once we understand or recall the relationship between operational theories and GPTs, this statement is just kind of obviously true from the definitions. So let's remind ourselves of those definitions, which we heard from John earlier. So the thing which I've been calling an operational theory would maybe a bit more precisely be called an unquotiented operational theory, because it's sort of like the process theories John was talking about before you do quotienting. And from this operational theory, we can then define a quotiented operational theory, which is basically the same thing as a GPT. And the way this works, as John mentioned, is you throw away the context information. So you pick one representative element of this equivalence class, and you call that S1. So GPT state S1 represents all the procedures in this class. And similarly, each equivalence class here gets represented as a GPT state, a single GPT state. And similarly for the measurements, I'm going to switch to talking about effects now. That's just a conditioning on a particular outcome of a measurement. And that's just a convenient thing to do. But the key is that when you do this quotienting with respect to operational equivalence, you're losing all the context information. So when you're just given the quantum state or the GPT state, you can't back out which of these procedures was done. All you know is that it was one of those which was in this equivalence class labeled by S1. So a quantum example, at the unquotiented level, the operational, what I'm calling operational theories, the procedures are just detailed list of lab instructions. So just repeating this again, maybe it's something like you flip a coin. Depending on the outcome, you prepare either the pure state 0 or 1, and then you forget about the outcome. So that's a way of preparing a particular ensemble mixture. And then maybe you have something similar for measurements, pass your system through a polarizer, check if some photocell clicks, whatever. So this is a very kind of minimal, and it doesn't really have much mathematical structure, right? It's just a list of instructions. It tells you what to do in the laboratory, but it has all this extra information. It tells you exactly how the procedures were implemented. In contrast, when you go to the quotiented description, you lose all that context information. In quantum theory, you recover just all this information gets lost, and you end up with just the density operator, which describes what's going on, the POVM element, which describes what's going on in the measurement case. And so now, imagine that you're working with your GPT description, as here. So I'm picturing here, this was like quantum theory when it's viewed as a GPT. It's just the density operators and POVM elements. If you can find an ontological representation of your GPT, well, that just means each density operator is mapped, each density operator or GPT state is mapped to a probability distribution over ontic states. Similarly, each effect in the GPT gets mapped to a response function. So if such a representation exists that reproduces the statistics of the GPT, well, then it's clear that you can just compose this quotienting map with the ontological representation map to define a map whose domain is the operational theory and whose codomain is the ontological representation, where you quotient and then you use this ontological representation. And so this map clearly is independent of context, right? The domain of the map has a whole bunch of context information, but the first step in this map is to quotient. So you lose all that information, so the resulting representations as stochastic processes in the ontological model can't depend on the context. So it just sort of follows from the relationship between these operational theories and GPTs is quotienting, and that's precisely what ensures that there's this equivalence between existence of any ontological representation of the GPT with any non-contextual representation of the operational theory. All right. So any ontological model for a GPT gives a non-contextual ontological model for the unquotiented theory which it came from. Yeah. Yes.
So if I understand you correctly, you say that so that there is only an ontological model if the theory is non-contextual, right?
There's only an ontological model for the GPT representing your operational theory if the operational theory is non-contextual. Exactly.
But how is this compatible with the fact that we have ontological models for quantum theory then?
So when you talk about ontological models, it's critical that you be clear about what the domain of that ontological model is, because as we've seen already, you can define ontological models for GPTs or for operational theories. So in one case, the domain of the ontological representation is the quotiented theory, the GPT. And that's what I've drawn here. That's the notion of ontological representation I'm using here. But earlier, we considered ontological models not of GPTs, but of operational theories. And it's much easier to build an ontological model of an operational theory because you can have things depending on the context. So we do have ontological models for all of quantum theory, but they're contextual. They depend, the domain of those ontological models is the unquotiented theory, which has all that context information, which you can then use to build the model. But if you take quantum theory as a GPT, and you try to build an ontological model of quantum theory as a GPT, you'll find that it's not possible. And Bell's theorem is exactly just a proof of this, if you think about it. Yeah, so maybe I should have been more explicit about that, that there's really two kinds of ontological representations. One has, and the difference between the two is the domain of the map. Which kind of operational theory are you trying to represent? Okay. And I'm just going to repeat this once more with a different visual, just because this is a really key point, and I want to make sure everyone gets it. So here we have that picture again of all the procedures in the operational theory. So here we have all the context information around. And when we quotient, we get the sort of GPT description, where we've lost all the context information. The ontological model is a map from this GPT to its representation. And here I'm just focusing on states. So it assigns a probability distribution to each of these objects. And so if we compose this quotienting map with the ontological modeling map, we get a map whose domain is different, right? This ontological modeling map has as its domain the quotiented theory. This one has its domain being the unquotiented theory. And the key is the composition of quotienting with that representation necessarily doesn't depend on context, because the first step of that, by definition, is quotienting. So you can see this epistemic state here is assigned to all the elements in the equivalence class by construction. So that's why we have this relationship between non-contextual models of operational theories and arbitrary ontological models of GPTs. All right. So in summary then, let's kind of tie this all back to classical explainability. An operational scenario is classically explainable if and only if, one, it admits of a non-contextual ontological model. We argued that from sort of Leibnizian kind of arguments. Or two, if its GPT admits of of any ontological model. And we argued that from kind of independent geometric considerations within a GPT. And three, if its GPT admits of a simplex embedding, where these two conditions were really just kind of different perspectives on clearly the same thing. And these are all sort of equivalent notions, so they're equivalent senses in which things can be divided into classically explainable or not. And I want to make a connection to what Matt said, and I want to note, as I sort of hinted at earlier, that a simplex embeddable GPT is just an epistemically restricted classical theory. So you start with a strictly classical theory, just this representation of probability distribution over a space with three ontic states, and you rule out some of the valid probability distributions and response functions by axiom, right? This GPT is just postulating that, for example, this epistemic state is not something you can prepare in the laboratory. So that's that claim that these things are not physically possible is just an epistemic restriction, like the knowledge balance principle would be an example of this. It's a particularly clear, nice, symmetric example of this, whereas what I've drawn here is a really ugly, complicated-looking example, but they have exactly the same status conceptually. And so maybe it helps even just to see how this works. So the Spekkens toy theory has four ontic states, these four here. And so the space of probability distributions over 4 points is a tetrahedron. So this is the dimension 4 simplicial GPT, would be the thing containing all points in this tetrahedron. Points in the simplex are valid probability distributions. And the way the Spekkens toy theory was constructed is to say, imagine that these are the only physically possible states of knowledge. So these are the midpoints, right? So this, for example, is the uniform mixture of this ontic state, of this, the distribution which has all its weight on one ontic state, and this one, yeah. So each of these vertices is just, each of these midpoints of the edges is corresponding to one of these epistemic states that's allowed in the Spekkens toy theory. So we can just draw that like this, because now it looks a bit more like the 6 points on the block sphere. And if we consider the convex whole of this, so all the mixtures of these, this forms a GPT, the state space of a GPT. It's an octahedron. And by construction, it's living inside the strictly simplicial GPT in dimension 4. So it's this kind of subtheory of dimension 4 simplicial theory. And the effect space is constructed similarly as just restricting the set of logically possible effects. So I really like this connection because when I first heard the Spekkens toy theory, I was amazed by all the quantum phenomena that it could reproduce. And it just led me to wonder, like, what's special about this theory? Like, could we, tomorrow, can you just come up with some new, completely other kind of toy theory which makes some other random kind of principles and suddenly it also reproduces a lot of quantum theory? Or is there something special about the Spekkens toy theory? And in some sense, to me, this is kind of the answer. It says the reason the Spekkens toy theory can do what it does is because it's a non-contextual model, and the scope of Spekkens-like toy theories is precisely the scope of all possibly epistemically restricted classical theories. Okay, so running out of time, which is fine. Yes.
Would you motivate, like, in plain words again, this very important assumption of being epistemically restricted? Like, how can I, why is that, I understand it leads to very interesting insights, but could you explain this a little bit more in plain words?
Yeah, I think there's, I guess, a number of ways to motivate it. If you've already bought into non-contextuality as an important principle to satisfy in a theory, in the same way that locality is an important principle, then you can motivate these epistemic restrictions by the fact that the only theories which can satisfy non-contextuality are the ones that have this epistemic restriction. But maybe that's maybe you want an independent justification. So I think largely I would say they're kind of motivated a priori. Sorry, not a priori, but a posteriori. So you look at how much of quantum theory can be reproduced, and they're sort of interesting because of what they can do. I'm not sure if there's sort of an a priori reason beyond that. It might get into the whole debate on Scientology and Sci-epistemology, which would be interesting to discuss, but I'll not say more now. I'll just say one of the main motivations is because once you consider it, then you see exactly how much of quantum theory it can reproduce. Yeah.
A question. The context can be anything. For example, imagine I wanted to have a super deterministic theory, just for fun, where the context goes back to the beginning of the universe or something like that. Could I build such a thing from this, with this, taking into account this kind of context, or the context is always something operationally defined? Yeah, I don't know if this question is.
It's not. The question isn't completely clear to me. You could certainly consider superdeterministic theories and ask whether or not they were contextual or non-contextual. I'm not sure if that has been done, but you could ask that question. Okay. So to kind of summarize a combination of my talk with everything Matt talked about, we have three kinds of GPTs, classes of GPTs that are interesting. We have the simplicial ones, defined by a simplex and the dual. We have the simplex embeddable ones, which are the simplex plus the dual plus a non-trivial restriction, or they subsume this case when the restriction is trivial. And then we have all the other GPTs, the non-embeddable ones. And we will often kind of refer to these two kinds of GPTs as non-contextual, although strictly speaking, that's bad terminology because, as we said, GPTs don't even have contexts. So you can't ask whether the representation depends on context or not. But they're associated to operational theories, which are non-contextual, whereas these non-embeddable GPTs are associated to operational theories that are contextual. And sometimes, more commonly, we're referred to these simplicial GPTs as the strictly classical ones, and these simplex embeddable ones as classically explainable, and the non-embeddable ones as non-classical. And we mentioned the two key properties of strictly classical GPTs are that all measurements are compatible, and there's a unique decomposition of mixed states. And we saw in Matt's lecture that these classically explainable GPTs, when you have this epistemic restriction on a classical theory, can reproduce a long list of phenomena that have in the past been, candidates for interesting intrinsically quantum phenomena. But we see that they're not really so intrinsically quantum after all. You can reproduce them with just this minor modification of the strictly classical case. And when you look at these non-embeddable GPTs, these are the GPTs which have sort of the intrinsically quantum phenomena, the really strongly non-classical phenomena like contextuality, computational speedups, non-locality, and so on. And also, as Matt mentioned, some specific quantitative details, like exactly how many states can you encode or can you teleport, what are the precise probabilities with which you can do no cloning or things like that. There's specific quantitative features of these qualitative phenomena, which are also proofs of contextuality. And we will discuss that in the next lecture. Do we want to end it there, Lydia, or? Okay. Thanks.
Let me just talk some logistics before I introduce the next mini talk. So today for lunch, you can pick up the sandwiches, which will be here at the door in a few minutes, and go wherever. But we only have the coffee lounge until 12:45. So just so you know, we do not have it in the afternoon. For the poster session, I will talk more about this later. But essentially, you can go anywhere in campus. We have these two rooms. This one and J6, or you can go to the cafeteria or wherever you want, or you can even go home as long as you have Wi-Fi. And a voice and video channel Discord for this. And I'll also give you a place to tell each other where you are in case people want to come and meet you in person to talk about your posters. Okay, so one of our sponsors is the Quantum Center of PTH Zurich. And where's
Do you have a mic and everything?
where's the microphone?
Here's one.
And Philip Hammerlander, which you know as a lecturer, Edith Page will tell us a little bit about it. So, give me a second.
What is it? Am I?
The microphone and this will take.
I won't take much of your time. Thanks, Lydia, for giving us the opportunity to present ourselves. So as Lydia said, the Quantum Center is a sponsor of this event, and we're very supportive of such events at ETH in general. And what I'd like to do is to give you a brief overview of what the Quantum Center is, what we're doing, and there might also be some interesting information for some of you, at least those who are planning to do their studies at ETH or are already doing their studies at ETH, or are generally interested in what is going on in quantum science and technology in Switzerland. And that's actually what I'd like to start with. So in Switzerland, we have a very diverse set of institutions doing research in quantum science and technology. You can see some of them that I consider to be sort of the most important ones on this slide. And the interesting thing about Switzerland is that it's really covering all of the aspects of quantum research, fundamental and applied research. It covers basically all fields and also all approaches in terms of theory, experiment, computational, but also what is going to be more and more important, especially if we talk about scaling up quantum technologies for instance, quantum computing, is the engineering aspect. But not only that, there's also a growing ecosystem of startups and established companies. So thinking of established companies, I take ID Quantique as an example, and then there's other companies like Zurich Instruments, QSaber, QNAMI, and so on, who are coming up with their own products that make new things possible. So within this setting, In the past 12 years, the QSID, Quantum Science and Technology Network, funded by NCCR, Swiss National Science Foundation, has been trying to keep these different institutions together. That is going to end now, so different quantum centers are forming across the country. One of them at ETH Zurich, the Quantum Center of ETH Zurich. There is also the Quantum Science and Engineering Center in EPFL. Another one is forming in the University of Genève. And in Basel, currently there is another NCCR going on about spin. And this is also, I mean, this is not necessarily a quantum center because it's an NCCR, but it's also has been forming in the past few years. So we're trying to connect and try to keep things up as they were and maybe evolve them. So now focusing on the Quantum Center at ETH Zurich, it's a getting together of 30 research groups from 6 ETH departments and also of the Paul Scherrer Institute in Villingen. Our mission is actually to coordinate scientific and structural research and activities in quantum science and technology, being a contact point for third parties, also for the public, and also try to foster collaborations within our center, but also with the outside and also with third parties like industrial partners potentially. This comes out of a bigger program that is called the ETH Plus program, part of which is new professorships, also technology development, and that goes under the name of the Quantum Engineering Unit, which is also sort of paid from the same sources, but only associated to the Quantum Center. And of course also it goes with the newly established Quantum Engineering Master's studies at ETH that I may say a little bit more later on. These are our 30 members, currently 30. We hope to grow a little bit. And what they cover is really many aspects of quantum research and technology. First and maybe foremost, quantum computing, but also quantum simulation, quantum sensing, communication, and in particular basic science. And that's maybe also the reason why the Quantum Center is very fond of being able to support such events, because this is, after all, it's a summer school about the foundations of quantum physics. And actually, even if you claim not to be interested, I think as soon as you do some sort of quantum research, you also have to think about foundations at one or another point. And you can also see this in the distribution of people doing research in our center. You see that almost all of them said that they are doing some basic science in some or another form. That doesn't necessarily mean that they like to philosophize about foundations, but at least they really, they have to engage with questions like these. Yes, so our director is Professor Andreas Wallraff. And these are the 3 people currently working for the executive office. That's maybe not such an important slide. That's maybe more important about the activity. So currently we're planning a conference in Davos for next month. We're also co-organizing the Swiss Quantum Days, which are sort of a continuation of the Arosa meeting. Some of you may have heard of this. This was a meeting from QSID in the past years organized, and since QSID is going to end, we're trying to keep that alive. And we also have student-organized events, Quantum Hackathon. We support summer schools, we support conferences, and so on. Good, so of course we were also interested in industry partnerships. That's maybe not so relevant for you. On the other hand, we also have education events. Maybe that's more interesting. So we're really open to bring quantum technology, quantum science in general, closer to people who may not know much about it, or maybe to people who are very interested in it and may also be interested in it in terms of using it. For instance, we have given lectures at the Risk Center. That's a lecture for economists mainly, but they were very, very keen about learning this. We have given a lecture about the IT for the IT trainees on a very basic level, but still, I mean, these are people who will hopefully sooner or later necessarily get in touch with quantum technology. Or we have also engaged with the Quantum Engineering Commission with presenting the basics of quantum theory for a hackathon. Now I come to something that is really nice also for the student side. So in case you were planning to do a master's project at ETH and you're a female student, then you can apply for the so-called Inspire Potentials Master Award. This is a substantial award over 6 months for people who are planning to do the master thesis at ETH. So you need to be enrolled when the grant starts, but you can already apply beforehand and then enroll at ETH later on. So in case that's something someone of you might be interested, I'm also happy to answer questions during lunch. Another thing for those of you who are already at ETH or planning to come to ETH, the Quantum Center is also in close contact actually with a student board. So we are having a group of very active students who are also organizing these student-organized events. The goal of the student board is to really connect the Quantum Center directly with the students and also have educational activities and events. And also use these ties to get better access to other academic and industrial partners. And as the first activities, for instance, two members of the student board can come to our conference in Davos and present themselves and also get involved actively in a panel discussion, so they really get integrated into the activities. Good. So that's actually the setting of the Quantum Center. I've presented some of our activities and our mission. There are two more things that I'd like to highlight, which are not directly connected to the Quantum Center, but in some sense, anything that is going on about quantum research at ETH will sooner or later be connected to us. And that is the first thing I'd like to present is, or to mention once more, is the Master of Science in Quantum Engineering. So there is obviously a very high demand of skilled engineers with a background in quantum physics in some or another way, and this will only grow. And you can already see this today. For instance, I hear that professors from very, very well-known groups at ETH struggle to get good postdocs because there is so much demand also from the industry side. You know about the big companies investing lots of money in this field. So it's already there, and that's not even the engineering part. So when it comes to engineering, it's even worse because there has not been any way of studying this in a targeted way. You could study physics, you could study engineering, but there was nothing in between. So this master is trying to at least contribute to remedy this lack of staff. And you can see that the student numbers are growing. It started in 2019, and I think in 2022 the numbers will grow again significantly. And the background can be physics or engineering. So I think that's definitely something that you could take into account if you like the physics part, but we're still more interested in the engineering of stuff and not so much in the foundations. Maybe I'm talking to the wrong people here, but that doesn't mean you shouldn't be interested in foundations. As I tried to point out before, I think these things go hand in hand. And the second thing is some advertisement. So ETH is investing a lot of money into a new building called HPQ, Q standing for quantum, as you can imagine, right next to the HIT building. And they're currently starting to build this, and this building will contain lots of room for state-of-the-art labs. So ETH is really investing a lot in this direction. They make the quantum technologies a focus of the future strategy, which I personally find great, and I think it's also great for both students and later on postdocs and maybe even other staff at ETH to really go in that direction. So I think the future is bright, not only at ETH, but in particular. And I hope I could tell you a little bit about the Quantum Center, and if you have any questions, I'm happy. I'm going to stay for another 15 minutes or so. Thanks, Lydia, for giving me the opportunity, and enjoy your lunch.